It's great. So let's get started. So this is it's an exciting day. I'm getting my booster shot today. My kids are getting vaccinated soon. So hopefully all of this is drawing to its conclusion. Not sure exactly what the state will be, but I feel so better about it at least. So you probably saw on the door on your way in, I guess the previous class had a COVID exposure in here. I assume it's been ventilated out at this point, but always please, stay cautious out there. So where are we? We are in the dimensionality reduction section of the course. We talked about the singular value decomposition and how to think about that for dealing with very high dimensional data, and how you're kind of getting a lower rank and a lower dimensional representation of this. The schedule, we did a little review on the first day of the section, so the schedule got a bit shifted. I'll talk about the connection to the Eigen decomposition today. And then today is the algorithms day in this section. Each of kind of the different techniques within data analysis will basically cover kind of the how to think about it, how to use it, and then one kind of algorithm how to compute it. And today we're going to do the power method, which is going to be it's going to be a very simple, very simple algorithm, but we'll see how its analysis works, and this will help kind of hopefully help you understand the concepts of PCA a bit better. Again, this part of the class on dimensional reduction, the algorithms will be quite simple once you kind of can picture the linear algebra, but conceptually, how to use them, how to think about them, this is traditionally, students have found this kind of tricky. And on the quiz 5 will be on dimensionality reduction, and you're not going to implement stuff, you're going to have to think about. So this might be a little bit trickier of a quiz, but we'll, if you're following along in class, hopefully everything is going to be okay. So let's get into it, continue kind of catching up. We're a little behind, but I think by the end today, we'll basically catch up and have a bit of slack in the class next Tuesday in this section. So we were thinking about data, and let's think about data point now, X in RD, and kind of the core concept was the projection onto B of X. And in this case, remember, we represented V based on this basis vectors up to VK. And I just want to review the way to think about this, because it just is an important concept. And so we'll think about, it could be in high dimensional space here, and I'm going to have some point X, and then there's some basis vectors. We'll think of V1. This is is a unit vector somewhere. So each VI is also in RD, right? And then you're going to have an orthogonal vector V2, and these are going to kind of make up this span, right? And what we're going to have happen is the projection is projecting X onto this span, the closest point on this span. So this is the closest representation, and we can write this projection of Bx as the sum of j equals 1 up to k of Vj times the dot product of, so Vj and X, okay? And I think it's useful to think about this thing as some alpha j of X, right? And the way to think about that is there's this distance is alpha 1, this distance is alpha 2, okay? And that is exactly this length of the projection onto those vectors. And then kind of the projection is just in this new basis here, right? So I can think of writing this as j equals 1 to k of Vj of alpha j. And these are really, can think of them kind of as coordinates. And so one way of, I can kind of represent this new B, this projected point of X as a point in this coordinate system. It's kind of like alpha 1, alpha 2 is kind of representing this point in this new coordinate system. If I was in the original coordinate system with the thin black line, I use the X coordinate, the Y coordinate, the Z coordinate to tell you where that point is. Now in a different one, it could be lower dimensional, it might be still d-dimensional, but I'm giving a new coordinate system. Alpha 1, alpha 2 tells me where this point is in the space. If this is the same dimensional, it's just a different representation of that point. If it's lower dimensional, it's kind of giving me a lower dimensional coordinate system there. Okay, and right, so this is kind of a useful kind of concept. And if we're doing V transpose, one more thing to think about, V transpose X, right? This was some operation that we were looking at here. You can think of this V transpose, maybe this were the right singular vectors coming out of this singular value decomposition, and you have a vector X, right? So the length here, this is length D, this is length D. This is a d-dimensional vector, and maybe I've got k of these. I've got k of these d-dimensional vectors, and the output, one way of thinking about this output here is going to be this vector. This is now a k-dimensional vector, right? So this is V transpose times X. If V transpose is k by D, then the output is k-dimensional. And if I have a single kind of Vj vector here, then this multiplication this corresponding Vj vector, this would be Vj, well, it's going to end up with a value here, alpha j, and alpha j is just the dot product of Vj and X, right? So each row of V transpose, I kind of take that X vector, which is tall and skinny. When I multiply, you can kind of think of turning it on its side and then kind of dotting it with each of those rows of V transpose. Each of the outputs of those rows is a single value. That's the alpha j. And if I have, because these are all orthogonal, it's giving me, because of this picture, it's giving me a new coordinate system. So if this was a D by D matrix, it was the whole V transpose matrix. This is V transpose sub k for only the top k of these. Then I'm only get a k-dimensional representation, okay? And if I had the whole V transpose, which was D by D, I'd get another d-dimensional representation. That's just kind of changing the basis, changing the representation. We saw a picture of that in the last lecture. Okay, so the projection, because I'm multiplying by these Vj vectors, which are again in Rd, this is still a full d-dimensional representation, but this is how I'm getting a lower dimensional representation out of this. A new coordinate system that captures, that spans the interesting subspace, and this is giving me my new representation. Okay, so this is this isn't new, but this is kind of another perspective of what we're seeing again. I wanted to just start this lecture giving this new perspective here, and this will be a little bit useful in what we're talking about in the lecture today. Okay, good. All right. So again, if there are questions, you can ask, and I can review any of these points. Okay, so what I want to talk about next is the eigenvalues and eigen vectors. Eigenvalues and eigenvectors, in most linear algebra classes, which you should have taken before for this one, much more likely to have covered eigenvalues and eigenvectors. So who's seen these all before this class? Okay, great. And who had seen the singular value decomposition before this class? Okay, so some people, but not everyone. They're very related. The eigenvalues and vectors are very related to the singular values and so singular vectors. And the way to think about that, these are only, again, if you remember, these are defined with respect to a square matrix M, and yeah, it'll be convenient for us to talk about this as a D by D matrix. Square meaning if I drew it as that rectangle, well, it's a square rectangle, same number of columns and rows. And we're gonna think about this, yeah, and so the eigenvalues and vectors are a relationship where you get where it looks like this, where V is going to be V is going to be a vector in RD, and we're going to kind of assume this is normalized, so it's a unit vector. Okay, and what's happening is if you multiply M by this vector, you get back a scaled copy of this vector here, and the scaling of it is known as the so this is the eigen value, and this is the and these are the eigen vector, right? So it's a special vector, it's the eigenvector, the one that you multiply by this square matrix, you get back this vector again. It's scaled, but there's some scaling going on, and that scaling tells you something about the length of this, and is the eigenvalue. And so, all right, okay. So how do we relate these to the singular value decomposition? Well, these eigenvectors and values are not. They're in the nice case, they're going to be exactly D of these pairs. Okay, so we're going to want to have D pairs. In the nice case, I'm going to have D pairs. Well, we'll say V1, V2 up to VD, and lambda1, lambda2 up to drew that the wrong way, up to lambda D here. Okay, and these are paired together, and we're going to have such that, again, each Vj is equal to 1, and Vj dot Vi is going to be 0 for I not equal to j, right? So these are going to give us this orthogonal basis here. Okay, okay. So in the nice case, I'm going to have D of these pairs, and the like with the singular values, we're going to have lambda1 greater or equal than lambda2 greater or equal to lambda D, and I'm going to say greater or equal than 0. Okay, in this case, you can have these, you might have some which are actually going to be so negative. You could have things which are actually going to be imaginary. Some weird stuff can happen. But we're going to deal with the case. We're going to focus on the case because this M is not going to come out of nowhere. It's going to be constructed by data in some nice way. It's going to be not just the original data, but it's going to be constructed in a way so that we're going to actually ensure that this is the case. If this is true, then we have, then this corresponds with it being positive, so definite. So this is true. It could be positive, so semi-definite. If the last eigenvalues can be equal to 0, but let's not worry about this case. We're going to say that in fact they're all going to be greater than 0. Okay, so we're not going to worry about the positive. So semi-definite case, we're going to concern ourselves with this nice situation with the Eigen decomposition. We don't want to worry about these other cases. Those are going to be a mess to deal with. And this M is not going to, we're going to construct the M. Okay, and we're going to do this in a particular way. We're going to say we have our input data is going to be A, which is going to be an N by D. And we're going to assume that A is full rank and that N is greater than D. Okay. We can switch D and N if you want to switch the roles of this stuff here, and I'll mention how to do that. We're going to assume it's full rank, and this means that kind of every data point we have, maybe there's a little bit of random noise added to it. So stuff does not exactly lie in a lower dimensional subspace. This is sense data. There's error in collecting it. It's not going to kind of have this special property where stuff magically lies in low dimensional space. If you add a little bit of noise to everything, that this generally won't happen. That's not the case. There's other techniques you can do. You can add like this ridge term that we're not going to get into class, but we're going to assume this. Okay, and then we're going to create M as A transpose A. Okay, A is N by D, so A transpose is D by N, right? And so A is N by D, so the result of this is a matrix in R D by D, and it's going to be rank D. It's going to be full rank. Because A was full rank, then the rank of this will also be D, be full rank. If it's full rank and it's real, then we're going to get this, and it's constructed this way. It's going to be so positive definite, and we're going to have this nice property that all the eigenvalues are going to be greater than 0. Okay, so we don't need to worry about all that other stuff that you might have learned about in the linear algebra class to deal with those other cases. We're going to deal with this nice case here. Okay. Okay, so now, okay, this is kind of nice. I want to kind of explain how the singular value decomposition of A is related to the Eigen decomposition of M. Okay, and the right way to think about that is to say, let's say that the SVD of A is equal to, say, U S V transpose, right? So if I multiply these together, I get back A, okay? And now I want to consider what happens if I do M times a matrix V. Okay, this is the same V from the singular value decomposition of A. And M is created in this way. Okay. Okay, and this will relate, this is kind of like where M times an eigenvector going to give you back a scaled eigenvector. And we'll kind of see that this happens. And we're going to do this by kind of expanding M as A transpose A. times V. And again, we can expand A transpose at A using the singular value decomposition. Okay. So we're going to get VSU transpose. Okay, if I take A, yeah, so let's just write the other one out. This is going to be USV transpose and V. Okay, so the V and the second one, the USV transpose, that's just from the singular value decomposition. If you have a transpose matrix and you break it into components, what you do is you swap the order of the matrix multiplication. So it's now VSU, and I transpose each term. So the V transpose turned to a V, the S, well, that was a diagonal matrix. So transpose didn't do anything. And the U turned into U transpose. Okay. Great. So now some cool stuff will happen. We're going to see that the U transpose and the U, well, these are orthogonal matrices. So when I multiply them together, it's going to give me an identity matrix. It's a property of orthogonal matrix. You're asking, why does the SVD give you this big U matrix, which all of these rows or all the columns to the right didn't really mean anything? Well, you end up getting this nice, it's an orthogonal matrix, and this is one of the nice properties that comes out. You also have V transpose V, and V cancel with each other. Okay? So when I put this back together, I get the V, and I get S, and I get S. There are identity matrices in between, but those didn't really do anything. Okay, so those kind of factor out. It's like multiplying by a 1. Okay? And S is a diagonal matrix, right? So when I multiply a diagonal matrix by a diagonal matrix, you typically just write it as VS squared. And this is just going to be where S squared is just going to be a diagonal matrix, which is sigma 1 squared, sigma 2 squared, up to sigma D squared. Okay, there's a little kind of some things you need to kind of check here. Remember I said that SVD, S was an n by D matrix, but the bottom was all zeros. And I've kind of played a little bit, you have to be a little bit careful what's going on here. You can kind of drop, I need those, in order to recover this product, USV transpose equals A, I need those extra zeros. But I'm passing through this n by n identity matrix. And so I kind of need them there, but once I've got rid of that, I can ignore those zeros again and pretend it's just diagonal. Trust me, it's not going to get in the way of anything. It's really S transpose here. But okay, so there's a little kind of playing with the dimensions going on here, but trust me, it's not going to matter because I'm just ignoring some zeros. Okay, great. So what has happened here is that I've gotten out M times V is equal to V times S squared, and S squared is a diagonal matrix. And this is neat. Okay, I've got the original big matrix M, the big square matrix we want to analyze, a set of orthogonal vectors, and I got those orthogonal vectors back just scaled. The diagonal matrix just scales. It doesn't kind of manipulate or change them. It just takes the first one and multiplies it by the first entry in the diagonal and so forth. Okay, and so if I look at each of the V's, gave me these right singular vectors. Okay, and what each of them is doing, I can look at each of these. What this is encoding is remember, this is a set of equations, right? For all j, I'm getting M times Vj is getting back Vj times sigma j squared. You guys in class can't see that, right? For all j, this is what I'm getting. That's the set of D different equations encoded in this system. And that means I'm getting back this eigenvector like relationship. So exactly, that means Vj is an eigenvector of M. But this case, I got Vj as the right singular vector of A. And so what I get out of this is that the jth eigenvalue is exactly the jth singular value squared, right? And also Vj equals Vj, except I used V for both of them, but this is the right singular vector, and this is the eigen vector. Okay? So the eigenvectors are the right singular vectors when M is composed as A transpose M. And the singular values squared correspond with the eigenvalues. Okay, so pretty cool. These are really, you know, if you construct your square matrix in this way, which is kind of a nice way to construct it, you get all the nice properties, then these are basically the same object. You can do something similar if instead I do M, I'll call this ML, is A transpose, which is now in R n by n, then ML has eigen vectors U1, U2 up to UN, and these are the left singular vectors of A, and it has eigenvalues up to lambda D. These are going to be the again, these are going to be sigma lambda j is going to be sigma j squared. So these are going to be the squared singular values. For lambda k, for k equals d plus 1 up to n, we're going to have lambda k equals to 0. Okay, so this will be a little bit different. If this is for n greater than d and A rank is equal to d. Okay, if d was greater than n, right? D was greater than n and rank was n, then n is going to be smaller, and I'm going to get all the singular values are going to be the eigenvalues, right? But because we're typically working in the n greater than d world, I'm only going to get the first d of them. The rest of them will be zeros. Okay. Okay, so I can do the same thing with the left-hand side as well. This is just if I took everything and I transposed everything, I'm really doing the same thing. I'm not going to kind of go through the details, but just to say, you can do the same thing with the left singular vectors as well. Okay. And okay. Or there's also something useful called an Eigen Decomposition. Okay, if I take a matrix M, I can write this as V L V inverse, where V is going to be V1, V2 up to VD. This is going to be, this is going to be so orthogonal, and L is going to be a diagonal matrix, lambda 1, lambda 2 up to lambda D. Right? These are going to be these are going to be the eigen values in the diagonal matrix. I can decompose M, and this is basically a singular value decomposition, but in the nice case when M is positive definite and it's square, basically the left and the right singular vectors are playing the same role here. Because V is orthogonal, V inverse is equal to V transpose here. If you take an orthogonal matrix and you multiply it by its transpose, you're taking really, you're filling up the V times V, this as the identity. It's really a dot product between the rows, and only if it dots with itself is at 1. If it dots with something else at 0, because they're orthogonal, right? So we're getting this property back. So this is an Eigen decomposition. Hopefully you've kind of seen this, something like this before. One reason I want to point this out, though, is because we needed to take an inverse when we were doing linear regression. In fact, that was a case where M was equal to A transpose A. If you remember, part of the computation for computing linear regression involved the inverse of this matrix. And this is equal to VL, V inverse, okay? And you can write this similarly as so V L inverse, V inverse. Again, like the transpose, it kind of switches the order and takes the inverse of everything. Okay, so I've swapped the order. So this V lines up over here, and I take inverse this V, which is already inverted. That it's uninverted. Okay, and this is equal to V L inverse V transpose, right? I can do the transpose, so that's something I can calculate. I still, in order to calculate this, I still need to calculate L inverse, but this is a diagonal matrix. So it turns out L inverse is going to be a diagonal matrix of 1 over lambda 1, 1 over lambda 2, and 1 over lambda d, right? So I can compute that as well. Okay, so if I can compute the Eigen decomposition, I can compute the inverse of this matrix, which really depends on the singular value decomposition or whatever of A, right? So these are all related. So we've now kind of figured out how to compute the inverse, which we needed for this. Everything else we talked about how to compute products and transposes and stuff. So we need this inverse to actually do the linear regression step. That was hidden beneath Python before now. Okay. But we still haven't computed the singular value decomposition or the Eigen decomposition, and that's what we're going to do next. Okay. And unfortunately, it's not going to be a closed form solution where we can just kind of do matrix multiplication or something. There are kind of ways to do that, but they're not as clean or as neat as this. We're going to talk about the power method. There are many algorithms to compute the Eigen decomposition or the singular value decomposition. This is my favorite one. It's the cleanest and simplest. It's kind of looks like, it's kind of like a gradient descent sort of algorithm. Okay. Okay, so what is the power method? Let me write this up, this algorithm. This is going to be our algorithm. So for the day, unless maybe this is also an algorithm for the inverse, but it's going to rely on this step. Okay, so 0, we're going to initialize. We're going to have some guess. We're going to call this U of 0 as a random vector in RD. Okay, how do I create a random vector? It's important that this is random, in fact. We'll see why a little bit about that. I'm going to create a D Gaussian random variables and put them in here. And I can then normalize it. A Gaussian random variable is something you can compute using what's called like a Box-Mueller transform from uniform random values, which your computer can generate. Okay, I'm not going to go into that. If you look in the book in chapter 4, which we skipped, it talks a bit about some of this stuff. Okay, but this will need to be a random vector. Let's say maybe it's a unit vector. Okay, this is our guess, a random initialized guess of what the first eigenvector is going to be. Okay, then we're going to have a for loop for I equals 1 to q. So q will be some number of iterations. Here I'm not going to have a little bit hard to talk about. Is it converged? It'll be useful just to use a value q here. And then there's just going to be one simple step inside this for loop. I'm going to update my vector. And I'm going to take the old vector, I minus 1, and I'm just going to multiply it by this matrix M. Okay? And then 2, I'm going to return U, Q, and I'm going to make sure it's normalized. So I'm going to divide it by its length. This vector might keep getting bigger and bigger and bigger every time I do it, or smaller and smaller and smaller. But it won't stay a unit vector. So the last step is I'm normalizing. So it's a unit vector. But that's it. That's the whole algorithm. All right. It looks too simple to be true. And the claim is that this will be, kind of approximately, and we'll talk about that, the first eigen vector v1 of M, right? And then we can compute the first eigenvalue as actually M v1 norm, right? So we know how to compute this. v1 is a unit vector, so the length of M times v1 is just the first eigenvalue, right? Yeah.
So would this be the same thing as just raising M?
Yes and no. Yes. So we will analyze if I took M to the qth power. M is a square matrix, so I can multiply it by itself. And yeah, so if I just took M to the qth power and multiplied it once by a vector, that gives me the first eigenvector. Yes. That turns out it's not the efficient way of doing this. This is more efficient. Yeah, so we can think of this as, equal to U, Q is going to be M times M. Each time through here, I multiply it by an M, right? And so it's equal to M to the power Q. This is not Q here. This is U0. Right, so if I multiply M by itself a bunch of times, I can say I raise it to the qth power, right? And so we're actually going to analyze what this looks like. Although that's not a good way to implement it. This is a matrix vector multiplication. That's the core step. The matrix vector, it takes time, the size of the matrix times the length of the vector. I need to take D dot products here. A matrix multiplication requires D squared dot products. Each of them takes O of D time, right? So this takes Q times D cubed. If I do M to the Q, this takes Q times D squared, which is faster, right? And so there people run this on some very, very large data sets, and this makes a, from being feasible to not being feasible, especially if there's sparsity involved and not. So this is a much better algorithm from an efficiency standpoint, but it's equivalent if we assume, ignoring the numerical issue, is equivalent to this other version in red here, where I take M to the power Q and I just multiply once. Okay, so this is to get the first eigenvector and the first eigenvalue. Before we, yeah, so this is the whole algorithm. It's kind of super simple. Let me point out before we analyze it. So if we want to recover all eigen values and vectors, this is only the first one, but we know that V1 is going to be orthogonal to V2 up to VD, right? So I know it's going to be orthogonal. So turns out what I can do is I can remove the contribution from this. And the way to think about it is it's easier to state if M is equal to A transpose A, right? And what I'm going to do is it's easier to remove the contribution of V1 from A. If I remove the contribution and I make that subspace is kind of has zero effect to it, then I can iteratively apply this on the rest. Okay, so what I'm going to do is I'm going to update A1, which is going to be, this is going to remove the effect of V1. Okay, and I'm going to compute this as A minus V1 transpose. A minus A times V1 transpose. What this is effectively doing is it's projecting all the data in A in the one-dimensional space that is captured by V1. That's what this term on the right here is doing, but it puts it in the form of an n by d matrix. Okay, by doing the V1 transpose. Okay, and then I subtract that, so I'm removing one rank from A. So now A1 can have one rank one lower, and then I will create M1 again by doing A1 transpose A1. Okay, and this will be the square matrix I got back again, which now has kind of rank one lower, and now I get V2 as the power method of on M1 Q, right? And then I found the second one, and this will have to be orthogonal with the first one, and then I repeat this. Okay, so if I can do the first one, I can factor out, and then I can repeat and get all the rest of them. So, yeah.
I was just wondering if there's an intuitive reason why the problem.
Yeah, great. So the rest of the lecture will be talking about that. Yeah, good. We still have about half an hour, which will be good. We're going to talk exactly that. And if we have time, there's a cool demo on the website about this in Python. If we don't, then you can kind of peek at that after class on your own. Yeah.
So we're going to do d squared and then once again, do that d more times to find every single one.
Yeah. So this found, I ran the power method once. I found too far. Okay. I found the first eigenvector and first eigenvalue, which is the same thing as the first right singular vector, same first right singular value. And then, and that took Q steps. Q is some parameter. Let's think of Q as 10 or 20, right? The more precision you want in the decimals, the more iterations of Q you want. Okay, and then that found the first one, and I need to factor that out. I factor that out, and then I put the resulting M1 back into the power method, and I get the second one. Then I factor that out, and so I do this d times. This kind of step, yeah, I do. Then lambda 2 is going to be M1 V2 norm, and then I'm going to repeat d times. right? And and this will get me all of them. Yeah. Okay, there are other ways of getting all of them at once if you care to do that. You can kind of compute a whole bunch of them so simultaneously in other ways. So those, you know, those methods get a bit more complicated. Not too much more complicated, but you should understand the power method first to really understand those. Okay. Okay, great. So let's talk about why the power method works. And I will, I think I'll have time to go through the whole proof actually, or just about, but I'll start with intuition and then we'll eventually, so get further along, we'll get more and more formal, we'll formalize it more and more. Okay, again, so we're going to, why the power method works. And again, we're gonna set that, let's just say, yeah, let's say, we'll just write it compactly as V1 is equal to MU0 to the M to the power Q of U0. This is the power method in kind of small number of symbols here. Okay, so we're going to analyze this. We're going to start by looking at this MQ. Okay, let's say, so let's say that the, say we know that that M can be written as the eigenvectors and values V1, V2 up to VD, lambda 1, lambda 2 up to lambda D. Okay, so let's assume that we have this knowledge ahead. This is, we're no longer solving for them, we're going to analyze this, right? So let's assume we know what these are. Okay, and the kind of okay, so the first thing we want to think about is that because V1 through VD gives us a basis, that means that we can write U0 as the sum of J equals 1 up to D of alpha J Vj, right? So I can write it in terms of there's some kind of basis V1, V2, you know, maybe V3, right? There's some basis here, and I can write U0 in this coordinate system. This is not the original coordinate system. This is a new coordinate system based on the V's. It's a basis that allows me to write U0 in terms of this coordinate system. Alpha J's are the coefficients here. All right. Okay, and in particular, so we know that these alpha J's are exactly U to the 0 times dotted with Vj, right? That's exactly what this coordinate system is. If I put U to the U to the 0 here, then it's just the dot products. This is going to give me these coordinates, right? This is alpha 1. That's just the dot product there. Okay, good. Okay, so okay, the first thing, which I'm not going to entirely prove, is that I'm going to assume that alpha 1 is greater than 1 over 2 times square root, well, this is D. Okay? It's 1 over 2 times square root D. So it's not too small. That the first vector, I just need this for alpha 1. This will be true individually for each of the alpha J's. This is true with some constant probability, right? At least probability half, with probability greater than 1/2. Okay. Remember, U0, the first, our initialization was random, right? It was random. And, you know, the way to think about this, I'll just give a little bit of intuition here. Remember, if this is V1 and V2, and I pick a point here, well, I can write this distance. This distance was 1. This is U. And remember, the length of U was equal to 1 because it was a unit vector. Okay, so this was, if we assume this was a unit vector, well, then kind of its coordinates in this new basis were effectively random, right? So, and there's some, by the Pythagorean theorem, I know that 1 is equal to sum j equals 1 to the d of alpha j squared. Right? I can look at its coordinates, and I know that the hypotenuse, in this case, it's a d-dimensional hypotenuse, but it's, or 1 squared, right? So 1 squared, which is 1, is equal to the sum of all the individual coordinates squared. Okay, so on average, each coordinate should be about, their d of them, about 1 over square root d. Okay, the average one should be about, it's about 1 over d, but that's squared, right? So the expected alpha j squared is equal to 1 over d, because this is random. If I chose it randomly correctly, that means that the expected, and I can get from this using something like a Markov inequality, although it's a little bit different than Markov inequality, but it almost works, that the probability that alpha 1 is less than this quantity, than 1 over 2 square root d, is less than 1/2. The probability is less. So with constant probability, I get something nice here. Okay, so I need to assume I'm starting my U1. What this means, and intuitively what this means, is that the angle, the initial angle between U0 and V1 is not too close to orthogonal. Okay, if this starts out at 90 degrees here, I'm in trouble. If it doesn't, that alpha 1 is larger than something that's not too small, I'm going to be okay. Okay, so I need to say that that's why I need to start randomly. If I start randomly, I'm probably not going to be too close to orthogonal to the first eigenvector I want to find. Okay, that's kind of the first step, right? I need to start there, and I'm not too far away. Okay, so that's kind of the first part of the intuition. The second part, so this is, I start alpha 0 not too far from V1. Okay, that's the first part of the argument. The second part of the argument is that has to do with stretching. So this is part 1. Part 2, I'm going to have to say that as I'm going to see what happens as I go from M to MQ. And what's going to happen is I'm kind of going to look at this this aggregate shape of my matrix. So if we remember this, we have the aggregate shape was this idea of V1, V2, and that I multiplied them by the kind of, if I multiply it by sigma 1, I'm going to get something like this, and V1 sigma 2, and there's going to be this overall kind of aggregate shape here, which is this ellipse that is representing my data. Okay, and I want to, and this is the aggregate shape of A, of M, A transpose A, right? And I want to see what happens to the shape when I go from M to MQ, or from even M to M squared. what's going to happen to the shape? Okay, so the claim is that for M2, I'm going to get a shape that's going to have, so first of all, it's going to have the same time V1 and V2 are going to be the same. It's going to have the same right singular vectors, eigenvectors, right? Those are going to be the same, but that it's going to look more stretched out. So it's going to be more stretched out. All right, so if I draw this a bit. Bit better here, right? I'm going to kind of get the same. So the claim is I'm going to get the same basis, but more stretched. And this is just going from M to M2. And remember, if I took an initial vector, kind of if this was U0, and I look at it, I multiply it by M, I'm kind of getting this is M U0. But if I do U0 here, it's going to be more stretched up to M U0. It's going to kind of end up getting stretched out more towards V1. And so if I keep doing this up to MQ, say M to the power 10, this shape is going to be so stretched that it's basically going to be a line. Now, if I started completely orthogonal, I'm going to stay completely orthogonal. But if I start anywhere that's not too close to orthogonal from V1, then I'm basically going to get stretched all the way to V1. Okay, so this kind of intuition of what's going on. Let's go through this a little bit with the linear algebra. Okay. And so the way to do is to look at what's happening with MQ times Vj. Let's look at the jth eigen basis here, the jth eigenvector. Okay, so this will be equal to M dot 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 M times Vj, which I can write as MQ minus 1 M Vj. Okay, but I know this is an eigenvector, right? So I know that this is equal, that M Vj is an eigenvector. So that's M Q minus 1 times Vj times lambda j. Okay? And so if I do this one more time, I can say M Q minus 2 times Vj lambda j squared. Right? Because I just factored out one of the m's and I turned it into, I get the vector back, I just scale it, right? So ultimately, this is Vj lambda j to the power q. Okay, so that means this shows that m to any power, any positive power here, is going to have the same eigenvectors. I'm not changing the eigenvectors. And the eigenvalues, they get scaled to a power q. So the larger ones get larger, the smaller ones get smaller. Okay? And this, again, this corresponds with the shape stretching, right? If I have the shape and I turn to make the larger eigenvalues or the singular values larger, that's going to elongate the ellipse. The ones less than 1 are going to get shrunk closer to 0. So that's kind of, it's a kind of explaining how this ellipse is being stretched and squeezed. Okay? Right, if it's less than 1, then if you take it to a positive power, it gets smaller. If it's greater than 1, a positive power gets larger. Is there a question? Okay, great. Okay, Good. So this is kind of capturing this intuition, and you can actually the Python script, if we get time, it'll actually show this happening. Just a few iterations, it quickly turns into a line. Okay, so let's now finally we can get to actually the kind of an analysis argument with the tools we have now. Okay, so I can write. So I'm going to write the output of the algorithm V, right? I can write this now. This is going to be M Q U0, but then I need to have to normalize it. Right? And now I'm going to expand MQ U0 using the eigenvector basis. Okay, I need to do this from the top and the bottom. One to D, alpha J, Vj, lambda J to the power Q. Right, and the alpha J's were determined by the initial value of U0, right? And then I've turned this as the kind of just right in the eigenbasis times the eigenvalues, right? Okay, and I need to do this on the bottom as well. So be a little bit of messy algebra, but it's not too bad. There are just going to be a few steps here, and just the norm of this, right? If I just take the norm, I'm adding up the components. But all the VJs are unit vectors, so I don't need to keep track of them. And I square this term for each component. I add them up. I take the square root. Okay, so this is, again, I'm just rewriting the algorithm. This is the entire algorithm captured in an equation here. Okay, and what we would like, right, is that the output is going to be close to V1, which is the first eigenvector. Okay, so we're going to now measure that. Say V equals MQ U0. I want to say V dot product with V1. And it might end up that I get I might get the negation, right? So I might get V is pointing exactly the opposite direction of V1. Remember this picture, if I started pointing kind of down here, I'm going to end up pointing towards the bottom left of the screen, not the upper right. V1 was up here, so I could have it so the dot product is exactly -1, and that's still okay. This is only unique up to the sign of these directions, so I need to take the absolute value. So if this is close to 1, the absolute value of V dot V1, I'm good. So I want to say I'm going to get close to 1, and as Q gets larger, I should get closer and closer to 1. Okay? Okay, and how close is this? Well, the first trick is that I can write the top part here as A1 lambda 1 to the power Q, and the numerator is the same. Or the denominator is the same. Okay, the reason the numerator is just this is I'm taking a dot product, V with V1. Well, all those terms, I'm adding up these the numerator, this part, these are scalars, and Vj is a vector, right? So this is going to be kind of an element in our D, right? Because I'm adding scaled vectors Vj, but the only one that matters is V1. I'm taking a dot product. Anything times Vj, where j is not equal to 1, is going to be orthogonal, so that's 0. So only the part with V1 matters, right? And that dot product is 1, because V1 and V are going to be unit vectors. So I just get the A1 lambda 1 to the Q in the numerator here. Okay, so this is the term I need to say is going to get very close to 1. Okay. Now I'm going to kind of simplify the denominator. I'm going to do some approximation of the denominator here. This is going to be alpha 1, lambda 1 to the q. And I'm going to replace this by, let's say, all of the terms. Let's look at the first one term that depends on alpha 1, lambda 1 to the 2q, right? That's the first term of the sum. I'll put a square root over this when I'm done. And then I'm going to get the second term. Well, I'm going to simplify this one a bit. Okay, so the A1, the alpha 1, lambda 1, that's the first term in the sum. The second one, well, there are actually d minus 1, but let's just say d, other terms. And the alpha j's, those squared, alpha j squared, they're going to add up to at most 1. So I'm simplifying here. I'm saying there are most d of them. They are multiplied by values adding up to at most 1. So I can say, well, they're just d of these terms, lambda 2 to the 2q. Okay, this is an approximation. This is going to be, so I want this to be smaller than the above term, right? So if I make the denominator larger, then that's okay. And this is going to be larger than the rest of this term, except for the first one I found. Okay. Okay, and now I'm going to do something again. I'm going to make the square root kind of make a little bit nicer, lambda 1 to the q. The first term, let's pull that out of the square root. And the second term, I will do lambda 2 to the q. Okay, so I've just kind of pulled stuff out of the square root, and I made these terms a little bit larger. Okay, and now I've got the A1, alpha 1 and alpha 1, and I'm going to try and kind of cancel these a little bit. This is equal to 1 minus, so I'm going to think this term looks like the numerator appears in the denominator. So if I subtract and add this from the denominator, I can factor out a 1. So it's going to be 1 minus lambda 2 to the q square root d plus alpha 1 lambda 1 q plus lambda 2 to the power q square root d. Okay? So I've just done some algebra. This is just some fraction algebra. And then I have one more step, and then I'm done, and we can analyze this. It's going to be 1 minus 2d times lambda 2 over lambda 1 to the power q. Okay. This last step comes because I can now basically, I'm going to ignore the second, what am I doing here? Yeah, so, okay, so now I need to use my assumption on alpha 1. I'm going to use that alpha 1 we assumed was greater than 1 over 2 square root d. This was our assumption based on the random initialization, right? And so that square root d kind of I can use to cancel some stuff out here. And yeah, so if and it means that the first term is going to be, and I'm going to kind of ignore the second term. So I'm going to kind of ignore the second term here, taking lambda 2, and that's going to be to the power q. Well, lambda 1 was bigger than lambda 2, so I'm going to kind of also kind of ignore this term here. And then this, if I did this right, the square root d's should kind of, oh yeah, they go out in front as this d here. I'm 1 over square root d and a 2, and that goes into the numerator here. And I'm getting lambda 2 over lambda 1 to the power q. Okay, good. So let's Hopefully you followed it. If not, don't worry. This is the term we're going to analyze and think about a little bit. We're going to understand this last expression and the implications of that. But yeah.
So at the beginning of class, you said that we should assume that all the eigenvalues are greater than equal to, or we shouldn't be instead be assuming they're greater than. Lambda 1 is greater than.
No, this works if lambda 1 is equal to lambda 2. I can always, in this case, I'm going to, yeah, so I want to make that larger. Yeah, why can I get rid of that lambda 2 to the q term? Let's see, if I make this smaller, yeah, I'm subtracting that. Okay, right. So I'm subtracting this. So I want this term to be smaller. So I want this whole expression on the right to be larger. And that means I want the denominator to be smaller, and I can drop it. So I'm dropping this term because I'm subtracting now. And so I just dropped that term. And then I plugged in this value for alpha 1, and I worked out this expression. Yeah, so I didn't need that property. I mean,
Yeah.
they can be equal, it works out.
Sorry, I was just wondering if it's going forward. Is it lambda 2?
Yeah, okay, right. Good. So let's look at this expression now. This expression kind of tells us how fast it's converging and if it converges. This works well if there's a gap between the first and the second of the eigenvectors or of the singular eigenvalues or the singular values. If lambda 1 and lambda 2 are about the same or are exactly the same, then this algorithm is actually not necessarily going to converge. It will end up finding a vector which will be in the span of the first and the second eigenvectors, but not necessarily the first one. Then the ordering between them doesn't really matter so much. If there's a drop between the second and the third, then you'll say, well, it'll be in the basis of the span of the first and the second eigenvectors, but not in the third or anything else. So anywhere there's a gap, you can get some similar sort of kind of separation of the convergence, but only of everything above. Yeah, so you can get into that analysis and when can you recover all of them? There has to be gaps between all of them. Otherwise, there can be ties and those take longer to resolve. But yeah, so that's what this is saying. The convergence, this is saying that the convergence depends on the gap or the ratio between lambda 2 over lambda 1. Okay, so if this ratio is very small, meaning lambda 1 is much bigger than lambda 2, then this converges exponentially fast, right? Every step, right, I'm making, say if this is 1/2, lambda 1 is twice as big as lambda 2, then every step I go down by a factor of 2, right? And you guys all know kind of, exponents and logs and so forth. This is a pretty fast convergence here. Okay, and you see this in practice. This is basically the right bound, and almost any algorithm for computing these is going to have a similar sort of challenge of resolving things if the eigenvalues are close. This is not specific to this algorithm. This is just, well, I have to determine which direction is the most important, and if there are two that are basically tied, well, then it's a lot harder to do it. Okay, yeah. So again, the main takeaway is the convergence of the first one will depend on the ratio between the first and the second. So eigenvalues, and it goes down exponentially with Q. The stretching really, like this case, this ratio is probably 4, right? So it's going down by, by a factor of 4 every step. I'm getting a factor of 4 closer, right? It's the way of thinking about it. Okay, cool. I think we have time to just go through this demo really quickly. Let's go see it. This was This was put together by a former or a PhD student of mine who actually, he took the first version of this class when he was an undergrad. So Benway Shi, he's now he was a TA for this class at some point later on. And so again, this is the full power method right here in the algorithm. Same thing we said before. Okay. And you can get a random normal vector here for you, right? That's built in. Okay, and this is, yeah, so I'm starting for the random A matrix, and then B is my M matrix. So this is A transpose A, right? And I can compute the eigenvalues in these ways. You can see them printed out, but let's go see how well the power method works. The power method, the result, you know, after 4 steps, right, I'm getting very, very close here, right? I'm getting, this is the first eigenvector, and it ends up being pretty close here. You know, calculate the distance and using the norm distance. So it's really 4 steps did really well. Okay, let's see a visualization. This is, I think, pretty cool. All right, this should plot this is supposed to plot, let's try again. Yeah, okay, I plotted the first 4 points. This is a 4-point data set. And the first eigenvector scaled by the eigenvalue, or the right singular vector, is this red line, and the second one, the green one. You see the most variation from the origin is much bigger in this direction than that, right? Okay, and now we can kind of illustrate this algorithm. And the idea is we don't know where this random U0 is going to start. So we drew a bunch of guesses of where U0 would start, and they're unit vectors, right? And we colored them in different ways. These are possible starting points, okay? And so example, take the yellow one right here. We're gonna see what happens when I multiply these initial starting points, guesses of U0 by the matrix, and see how they get stretched. Okay, should be the first iteration. And so I'm running the iteration, the power method for each of those dots as the starting point. So you can kind of see that there's some randomness. The old ones are kind of inflated, and the new ones are kind of really stretched out, right? If I started right at this along the eigenvector, I basically stay there. If I stayed here, I kind of get shrunk and stretched this way, right? So I'm stretching out. This is only 1 step, right? If I do 2 steps, Okay, 2 steps, you know, it's almost a line here, but it's not quite. You can still see some gap there. And if I started in the wrong spot, I'm still gonna, you know, the directions, any one of these points, even though it's not all the way up here, it's pretty much along the line. So it's pretty much points in the right direction. But we'll see if I do one more step here, it's gonna be kind of very much in a line. Right, and that's what we saw. We ran this 4 steps at the beginning, and we got this kind of, yeah, you can't even see it anymore. I think he normalized these, and you get these points. So almost everything after normalization is right along the first singular vector, or it's negation. Okay. Okay, one more cool thing. Let's see if we can run this. If you do it as the algorithm is stated on very big data, something goes wrong. Okay, if I do it now, a 10,000 by 1,000 matrix A, something's going to go wrong here. Here, I'll just kind of jump to the end here. What happens is that these vectors, they get too big. They get too big, and I get all sorts of weird kind of numerical imprecision. So you can change it by basically just normalizing every step. I keep the same direction, but now I keep them from getting too big, and now this works fine. So everything works out. You can go through it and see it a bit more on your own, but just a little cute demo here. So great. So let's stop there. So the power method, kind of how to compute stuff. Hopefully the proof gave you some intuition as well. And then next lecture on Tuesday, we will see kind of how to solve the initial dimensionality reduction problem, which we actually haven't quite solved yet. We're missing a step. And we'll see one application of this. This SVD and PCA are kind of going to be the backbone of a lot of techniques in data analysis. And we'll see just one very simple one called multidimensional scaling. But the book will cover a bunch more of these as well, but they're a bit more advanced. Okay.